Okay, so we said divergence is the dot product of the del operator and our vector field F. And the divergence theorem tells us that a surface integral is equal to a triple integral. Okay? A surface integral over some closed, the circle on the integral sign means a closed surface, like a sphere, like a cube, a box, or a prism, or something like that. A plane is not a closed surface. That would be an open surface. Over the surface integral over a closed surface S is equal to a triple integral over a region of integration D. D here doesn't mean divergence. D means a region of integration for a triple integral. Okay, we've used D for that for a long time, even before we introduced divergence. D here does not mean divergence. Okay? But this surface integral over this closed surface is equal to a triple integral over a region of integration D, where this region of integration D is the region enclosed by this closed surface S. So if S is a sphere, the surface of a sphere, D is everything inside of that sphere, the whole volume inside of that sphere. So we've got the surface integral over S is equal to a triple integral over a region of D, where D is, everything inside of S, of the divergence of that vector field. And we said, well, that gives us now two options. If we're asked to calculate the total amount of flux, and remember a surface integral gives you flux. If we're asked to find the total amount of flux passing through some closed surface S, we can calculate the surface integral, okay? And we remember there's four cases: spherical surfaces, cylindrical surfaces, planar surfaces, planes that are parallel to axes of our coordinate system. That was the third case. And then the fourth case is basically any surface S, and we use the gradient or the partial derivatives of F to find that, to find n hat. Okay, we can do that. We can calculate the surface integral to find the flux, or we can use the divergence theorem, which means instead of calculating the surface integral, we can calculate this triple integral instead, because very often calculating this divergence, it's just a dot product. We're just finding some partial derivatives and adding them together. Okay, that usually is pretty easy to do. And depending on the region D, this triple integral might be very easy to do as well. Okay, it might be easier than the surface integral. Okay, and if we look at what's going on here, well, this calculates the total amount of flux passing through this surface. And what do we got on the right side here? Well, we said that divergence is what? Divergence is equal to flux density. Flux per unit volume, okay? And del dot F tells us the flux density at a point in our region D. This, at some particular value of x, y, z, gives us the flux density at that point, x, y, z, which is somewhere inside of D. Okay, if I take that and multiply it by a very small volume, if I take flux density and multiply it by volume, what do I get? Flux, right? Flux per meter cube times meter cube gives me flux, right? So that means everything inside here becomes flux. I'm calculating up the flux that is basically being generated inside of this volume D. Right? And if I have 10 units of flux being generated inside of D, where is that flux going? Well, it's going to have to pass through this surface S, right? If I've got a source of flux inside, say S is a sphere, and I've got a source of flux inside of that sphere, creating, 10 units of flux. Well, where's that flux going to go? Well, it's going to pass through the surface of the sphere as it travels outward, right? Or if I get a negative number here, that means I got a sink inside the sphere. So I got flux going into the sphere, crossing this surface S of the sphere. Okay, so physically that's what's going on. Okay, for the final exam, all you got to know is, if you're asked to calculate a surface integral, you got two ways you can do it. If you're asked to use the divergence theorem to calculate the amount of flux passing through S, that means calculate this. Okay? Use the triple integral. Using the divergence theorem to calculate flux means calculate this, because you know it's going to give you the same as that. Okay, any questions about that? That's the divergence theorem. Okay, and then there's a couple of examples from electricity and magnetism you can look at if you're interested. Let's get to the last topic, which is the last theorem we got to learn, which is Stokes' theorem. And Stokes' theorem is just another theorem that equates two different types of integrals to each other. And it has applications in a number of different fields as well. I first saw it in a course that studied the gravity field of the Earth. Stokes' theorem is used a lot there, looking at the gravity field of the Earth, and there's lots of other applications. Stokes' theorem is simply this. Okay, what is that? Have we seen that before? Yes, we have. If that doesn't look familiar to you, you got a lot of studying to do in the next 2 weeks. Right? That's a vector line integral. We're integrating a vector function f along a closed, again, this circle here means it's a closed curve. If there's no circle, that means it's a curve that doesn't come back on itself, right? This is finding the vector, the integral of a vector field f along a closed curve C. Okay, we did that, I don't know, at least a couple of weeks ago now, I guess. Okay? Stokes' theorem says that that is equal to a surface integral over a surface S of this. Okay, it's a surface integral. So we've got something dot n hat dA, and that something is what? What did we call this? Anybody remember? The curl. This is the curl of F. This is the divergence of F. Okay, there's some symmetry going on there. They both have the del operator. One's a dot product, the other's a cross product. We talked about curl of a vector field, right? That has to do with rotation at a point due to that vector field, right? We threw sticks in rivers and all that stuff. Okay, that was curl. So Stokes' theorem tells us that if we need to find, for instance, the amount of work done by a vector field F on some mass that follows a closed curve C, we can find the line integral, right? We talked about that when we introduced the vector line integral. That is one physical application of it, calculating the work done by this vector field F along a curve C. Okay, well, this Stokes' theorem tells us there's another way to calculate that. And that is by taking the curl of F and integrating that over a surface S, finding a surface integral. Okay, divergence theorem took a surface integral and equated it to a triple integral. Stokes' theorem takes a single integral, a vector line integral, and it equates it to a surface integral. And so the question here is, obviously these two F's are the same. This F and this F, same F. How are C and S related? Okay, they have to be related in a certain way for this theorem to be true, and this is the tricky part. Okay, for a closed curve C, let's say curve C is just a circle in space. Okay? How many different ways can I go around that circle? 2, obviously. I can go this way or I can go this way. Right? So I can calculate this vector line integral here, either this way around the curve C or this way around the curve C. Right? Okay. So C can be oriented one way or the other way. What about surface S? If my surface S is just this, how do I orient a surface? When we did surface integrals, we learned how to orient a surface, right? We did that with a vector perpendicular to the surface. I can say my surface is oriented by this normal vector or by this normal vector, right? I had a choice. Okay? So surfaces and curves can be oriented in one of two directions. So C and S must be compatibly oriented. How do you spell compatibility? I'm going to guess that. Compatibly. C and S must be compatibly oriented for Stokes' theorem to be true. Okay? Okay, so let's say here is my curve C. It's just a circle. Okay, that's my curve C. And let's say curve or surface S looks like, I don't know, like this. So maybe I got an upside down bowl. That's my surface. Okay, and the rim of the bowl is my curve C. Okay, and let's say I orient C by drawing an arrow on it like that. Well, now for Stokes' theorem to be right, I have to come up with the right n hat for my surface S. My n hat at any particular point on that surface could be pointing out from the surface, or it could be pointing in, right? I got two choices. N hat, it's got to be perpendicular to the surface, but it could be pointing out or pointing in. Question is, which way is right for the way that I've drawn C? And we're going to use our right-hand rule to do that. Okay, my apologies to the lefties, but it's the right-hand rule. Okay, you're going to point your thumb in the direction of C. Your thumb is going to point in the direction that C is oriented. Your first finger, your pointer finger, I'll call it first because the next one I'll call second. First finger is going to point tangent to S. And then your second finger points in the direction of n hat. Okay, second finger points in the direction of n hat. I'm just going to scroll down a bit here so I can read so I can reach the screen. We'll go back up in a second. Okay, so if I take my right hand, I pick some point along the curve C. I'm going to pick this point right here at the front. And I'm going to point my direction of the curve C. Okay? My first finger is going to be tangent to this surface. So if my surface, our surface like that doesn't look that, but if this is my surface and it's curved like this, right? And here's curve C along the rim. I'm pointing like this. This first finger is going to be along tangent to this plane here. I'm not going to point it like this or like this. I'm going to point it so my first finger sort of lies on the surface. And then this is getting hard. Then my third finger points in the direction of n hat. Okay, so if my surface is sort of this upside down bowl, like this, I'm going to point my finger along the surface of the bowl, and then n hat points out. Right? So, how do I draw n hat for the surface? Would it be coming out of the surface or into the surface? Well, I just told you. Thank you. I just said out, right? So right here, I'm going to do it over here, right? Sorry. Let's say I do it right over here. N hat's going to be pointing out like that. Okay? Of course, if I go higher up on the bowl here, n hat always has to be perpendicular to that surface. So up here, it's going to be pointing out like this. Up here, it's going to be pointing out like this, right? It's always perpendicular to the surface. Okay? Everybody got the right-hand rule? Thumb points in the direction of C. First finger points tangent to the surface. Third finger, first finger, second finger points in the direction of n hat. So if I turn C around the other way, if I said C actually goes in that direction, Well, then my thumb points in the direction of that. My first finger, again, is tangent to the surface. Second finger, and half. Goes in now, right? So in that case, n hat would have to look like this. I guess I should do dotted lines because it's inside. Okay, so that's the trick. So if you're going to use Stokes' theorem and make a vector line integral equal to a surface integral, you got to orient them compatibly. Now, there's conventions, of course, okay? Remember when we did surface integrals and we talked about closed surfaces, we said conventionally people say n hat out is positive when you're just doing a surface integral, right? Same thing with curves. Traditionally or conventionally, if we've got some curve in 3D space like this and we're going to right, and this is sort of the XY plane, kind of like this. We say, okay, curve C is going to go like that, so that if I use my right-hand rule like this, right, n hat comes out. Okay, so we typically say that. Because the surface S doesn't have to be a bold, right? Surface S could be planar, it could be a plane, which is kind of what I drew here, right? So my surface S is in here. So the other way, in that case, you know, if this confuses you, because there's three things to remember, I get it. If you're lucky enough that your surface S is a plane, and the curve C goes around it like this, you can just curl your fingers in the direction of C, and your thumb points in the direction of n hat. In this case, sort of up or out. Okay? If curve C was going this way, surface S would be oriented in like that, with n hat like that. Okay, any questions about that? That's all you got to remember. Okay, so the right-hand rule. Okay, well, things can get a little bit more complicated with certain types of surfaces. For instance, what if we've got a cylinder? In my example up here, how many curves bounded this surface S? We say curve C here bounds S. That means it limits S. Right? There's only one curve that bounds this upside down paraboloid. Right? If I used a curve down here, well, then the paraboloid would be bigger. Right? It's the curve C that bounds it. How many curves bound a cylinder? Two, obviously, right? We've got a curve up here now, curve C2, and we've got a curve down here, C1. We've got two curves that bound this cylinder. Where's the surface of the cylinder? It's the wall of the cylinder, right? This is an empty toilet paper roll, right? The air at the end of the roll is not part of the toilet paper roll, right? It's air. The cardboard sides are part of the toilet paper roll. So our surface S is the wall of the cylinder. And it's bounded on two sides by two curves, right? So we've got a curve 1 and a curve 2. If we want to use Stokes' theorem to calculate the flux passing through that surface, by calculating the flux passing through the surface S, we can either use a surface integral or we can use a Stokes' theorem, and in that case, we have to calculate two vector line integrals, one around this curve and one around this curve. And the sum of these two vector line integrals around curve C1 and C2 will be equal to the surface integral of the curl of this surface S, right? Because remember, we've got, this is Stokes' theorem. Okay? So because our surface S now is bounded by two curves, this is not just one vector line integral, it's two added together. The one around C1 plus the one around C2. So if we're going to use Stokes' theorem for this case, we've got to, again, orient both C1 and C2 properly with respect to S. So if, for instance, I choose n hat for my surface integral, S, to be like this, out. Okay, that's what I choose for n hat, instead of in. Well, that now constrains me to the directions that I got to choose for C1 and C2 in order for Stokes' theorem to be correct. And my right-hand rule. So use your right hand, and you tell me which direction, let's start with C1. Which direction do I have to orient C1 so that it is compatibly oriented with respect to the n hat I chose for S? Do I draw an arrow going this way, or do I draw an arrow going to the left at the front part of C1? Right or left at the front of C1? To the right, I hear. Well, if I point my thumb in the direction of C1 to the right, my cylinder wall goes straight up. Yep, and hat would come out. Correct. Okay, anybody not get that? Okay, what about C2? How do I have to orient C2? That way means to the left. Yeah. At the top, at the front edge of C2. I got one vote to the left. 2 votes. 3, somebody doesn't know. Oh, okay, they're doing the right-hand rule, sorry. I thought they were doing this with the thumb, which kind of meant, I'm not sure. Up. To the left, right? I gotta lower this again. So if I point my thumb to the left and my first finger has to point down because my surface S is down here, right? Then my second finger would point out in the direction of n hat, correct. To the left. Okay, so now Stokes' theorem in this case would be okay, so that Stokes' theorem now tells me that the sum of the vector line integrals around C1 and C2 is equal to the surface integral of the curl of F along the surface S. Okay, and what if some nasty professor puts a question on the final exam and says, calculate or show me what Stokes' theorem is if I insist that C2 looks like that. N hat remains out, C1 remains in this direction, but C2 is also in that direction. How is this going to change? Well, what happens when you change the direction of orientation on a vector line integral? It'll be negative. You go in the opposite direction, you get the negative, right? Just like when you multiply a vector by -1, what have you done to the vector? You've changed its direction by 180 degrees, right? Same thing with a vector line integral like this. If I calculate, we're talking about C2. So if I calculate this vector line integral in this direction, I'll get some number. If I calculate the vector line integral of the same f in this direction, I'm going to get the negative of that number. Okay? So if I insist that you do it this way, well then this just becomes minus this one. We'll still make Stokes' theorem correct. ... Same stuff. Okay? Okay, well, there's a piece of good news here that I haven't told you yet. Why in the earth would we do this to calculate this? Right? Because, this looks like a lot of work. You got to do a cross product, that takes time. This is a surface integral, so we got to figure out what's n hat, what is dA, what type of surface is it, right? Surface integrals, there's a lot of work involved with them. Sounds a whole lot easier to do a vector line integral, right? Just parameterize this curve, make it a function of t, make f a function of t, right? Find out what f is along this curve, make it a function of t, do the dot product, you're done. Single integral sounds a lot easier. The beauty of Stokes' theorem is that it is true no matter what surface S you choose, as long as that surface S is oriented compatibly with the curve C. So if I've got a curve like this, a circle again, that's my curve C, I can choose any surface I want as long as it's bounded by that curve C. So I can choose, this upside down paraboloid, or I could choose a surface like that, or I could choose one that's kind of skewed if I really want to make my life miserable, or I could just choose, oops, that's not what I want to do, sorry. Or I could choose this surface, right? That's a surface that's bounded by C. So the beauty of Stokes' theorem is you can choose any surface S that bounds C as long as it is compatibly oriented. Compatibly oriented. So naturally, you're going to choose really simple surfaces, which makes calculating the surface integral really easy. Okay, obviously, if some really bizarre surface will make the surface integral, but why would you choose that? So you're going to choose the simplest surface possible to bound that curve C. Right? Choose simple surface S. For instance, that one. Just now your surface S is a flat plane. It's a circle. Okay, and we're going to do some examples. One more thing, though, is we should let you know the relationship between Stokes' theorem and Green's theorem. A lot of these theorems are related. You'll remember Green's theorem was what? It applies to 2 dimensions. And Green's theorem told us that a line integral was equal to a double integral, right? In 2 dimensions. Okay, well, if curve C, over which you calculate this line integral, is in the xy plane, and if our surface S is that part of the xy plane, bounded by C. So maybe C is a circle in the xy plane. So S is just the interior of that curve. It's the circle, right? C goes along the edge of a circle in the xy plane, and S is just the circle itself, the whole circle in the xy plane. Okay, and we orient them compatibly. C goes in one direction, and n hat for the S goes in the proper direction. Well, that curl of F in the surface integral in Stokes' theorem is just going to be equal to, and you can check this on your own if you want, the curl of F dot n hat, right? So you got curve C going, again, if this is the xy plane, the table is the xy plane, and my curve C is a circle going counterclockwise, then n hat is going to point up from the xy plane, right? N hat is just going to be k hat. The unit vector pointing in the z direction, k hat. That's a k, believe it or not. Let's try again, k hat, okay? Well, then this is going to be equal to this curl of F dot k hat is simply going to be equal to this, partial derivative of n with respect to x minus partial derivative of m with respect to y. Right, again, where F is equal to m n p. That's the only term you're going to get. If the curve is in the xy plane and if the surface is in the xy plane. That's all you're going to get. So then according to Stokes' theorem, this line integral around the curve C is going to be equal to a surface integral of del cross F dot n hat, which is k hat in this case, which is going to be, I just said, is this partial derivative minus this partial derivative. dx dy, dA, which if I'm just using xy coordinates, it's just dx dy. Okay, over a region R, which is just my circle. The surface S is a circle in the xy plane. That's the region R. So what does that look like? That's Green's theorem. So if you take Stokes' theorem and you reduce it down to 2 dimensions only, you get Green's theorem again. So all these things are kind of related. Okay, so that's just a interesting idea or fact. Okay, let's look at some examples. Any questions so far? Okay, we've got F, which is given to us to be y I hat minus x j hat. So there's no z component to this vector field F. And our surface S, we are told, is x squared plus y squared plus z squared is equal to 9. So what is that? X squared plus y squared plus z squared is equal to 9. A sphere centered at the, with radius, right, okay? But one more thing, z is greater than or equal to 0. So what does that give us for a surface? If we take that sphere and we restrict z to be positive or equal to 0. Half a sphere. The half of the sphere that sits on the xy plane, right? So if I would draw that, that's my surface S. So what is the curve C that bounds that surface? Well, obviously it's this circle in the xy plane, right? Which is a circle of radius 3. Okay, well, first task is we're gonna prove, computationally we'll prove Stokes' theorem, which means let's first calculate the line integral part of Stokes' theorem, then we'll calculate the surface integral part of Stokes' theorem, and we'll see if they're equal. Okay? So we're gonna start with the line integral. Along C. So let's choose this direction for C. This is C and this is S. Let's choose that direction for C and let's calculate the line integral. Okay, so we're going to calculate this line integral f dot dr. So to do that, we need to parameterize our curve, right? So how do we parameterize a circle? This goes way back, early October, maybe even late September. How do we parameterize a curve? We make it a function of one parameter, t, or what makes sense with a circle? Theta, right? Because we're going to use trig. It's a circle. Whenever you see a circle, you think trig, right? So how do I parameterize? Well, I'm going to parameterize by creating a position vector r, right? This r here is a position vector. It starts at the origin and it points to a point on your curve. And I'm going to make it a function of theta, which is the angle from the positive x-axis in this direction, right? So when theta is equal to 0, r points from the origin to there. When r starts getting bigger, it starts pointing here and keeps getting bigger. It points like this, right? The tip of the position vector traces out the circle as theta changes. We did that way a long time ago. It's a position vector, function of theta. And what is that equal to for a circle like that? If I start at the positive x-axis and I go counterclockwise, what's the x component of a circle? 3 cos theta, right? What about the y component of that position vector? Thank you. There's no z component, right? We put a 3 there because the circle has a radius of 3. So when theta is equal to 0, the x component of this is going to be 3, 0. Pardon me, this vector is going to be 3, 0, which is going to point from here to there. When theta is equal to pi by 2, this is going to give us 0, 3, which points there. Okay? Okay, so we've got a position vector. To do the vector line integral, you'll recall that we need the derivative of that. We need dr, which is basically dr by d theta, multiply that by d theta, right? So you take the position vector of that vector, you get another vector. You get minus 3 sine theta d theta. You get 3 cos theta d theta. Right? dr by d theta would be 3 sine theta, 3 cos, or negative 3 sine theta, 3 cos theta. You multiply both sides by d theta, you get that. Right? That's the dr we need up here in our vector line integral. Okay, so far so good? Okay. We also have to parameterize our vector f. When we calculate the vector line integral, we only care what f does along the curve C. Okay? F has components of y and x. Well, by doing this, by writing this, we say that everywhere along the curve C, x is equal to 3 cos theta and y is equal to 3 sine theta, right? So we substitute those in here. This x becomes 3 cos theta. This y becomes 3 sine theta. That's what f does along the curve C. Okay? Of course, not on C, somewhere else, x and y does something different. But along the curve C, this position vector tells us x is equal to this and y is equal to that. So we substitute these values into f because we only care what f does along the curve when we're calculating this vector line integral. So f now is going to become y is equal to 3 cos theta. And negative x means we got 3 sine theta. Did I write that correctly? Y is equal to, oh no, I was looking at dr, pardon me. That's not right. Okay, I need y here. Y is equal to 3 sine theta. And now I need negative x, and x is equal to 3 cos theta, so I have negative 3 cos theta. Okay, well now I can just take the dot product. F dot dr is equal to 3 sine theta minus 3 cos theta dot dr, which is negative 3 sine theta d theta, 3 cos theta d theta. All right, you do that, you're going to get a bunch of sine squares plus cosquares, which of course equal to 1, and that is going to simplify pretty easily to minus 9 d theta. So now my vector line integral is simply minus 9 d theta. Okay, and what are going to be the limits for theta? Sure, use 0 to 2 pi, or minus pi to pi. If you want to be difficult, pi by 2 to 5 pi by 2, just integrate over 2 pi, 0 to 2 pi, right? So that's not difficult. We're going to get negative 18 pi. Okay, so that was a relatively painless vector integral to do. So now in the final exam it says use Stokes' theorem to obtain the line integral. That does not mean solve the line integral again. Okay, you already did that in part A of the question. Use Stokes' theorem to calculate the line integral means calculate the surface integral that Stokes' theorem says the line integral is equal to. Okay? So we're going to calculate the surface integral. First, we've got to find the curl. We need this. Okay, again, that's going to be pretty simple because, well, first let's go up here. What is n hat? Oh, we don't even need n hat. We just find the curl of this here, del cross f of this. Right? So you do that 3 by 3 determinant, ijk, partial derivative of x, partial derivative of y, partial derivative of z, and then f, which would just be y minus x 0. Because of that 0, it gets pretty easy to do. Okay, we won't go through the gory details. Practice it yourself. You'll find it's simply equal to minus 2 k hat. Okay, so that's what it turns out to be. Okay, well now we got to put that into a surface integral, which means we need an n hat and a dA. We need to do a surface integral. So which of the 4 cases that we looked at should we use for this surface S? We said surface S is half of a sphere, so we should use the spherical case, right? Okay. We've got to figure out what n hat is and its direction. So we use the right-hand rule to compatibly orient S with the curve C. We chose to orient curve C going that way, which means n hat's going to be coming out of the sphere, right? So we got to choose n hat out like this. Or if we were at this point, n hat would go out like this. Okay, we're going to choose n hat out to be compatible with choosing C to the right, which is where we started. So we know that. We know the z component of n hat is going to be positive. It's not going to be negative. It could be 0 if we're looking at a point on the surface right down here. This would have a 0 z component. But everywhere else, it's going to be a positive z component, up, n hat, okay? Okay, and what is n hat equal to? If you look on your equation sheet for the final exam for a spherical case for the surface integral, it tells you it's equal to 1 over a x, y, z, where a is the radius of your spherical surface, which in our case is 3. So we write this. Okay, and we would not put a negative sign in that because that would then mean n hat points into the sphere. We just determined that n hat should point out of the sphere, so we leave it alone like that because this will have positive z component. Okay, and then dA. N hat dA for our surface integral. Again, we look on our equation sheet in the form for the final exam, and we see it's equal to a squared sine phi d theta. So a is 3, so 3 squared sine phi d theta is our dA for a spherical surface. So we got everything we need for our surface integral. Okay, del cross F was negative 2 k hat. And I'm going to put the 3 under that from n hat. Oh, pardon me. What are they doing here? Oh, yeah, I kind of, just let me erase that for a second. Let's do it one step at a time. What is n hat, del cross F times n hat? Del cross F dot n hat. What is that? Let's calculate that first. So take the dot product of this vector up here, which is this, with this. So the dot product of these two, what do I get? I get minus 2z times 1 over third, right? So I get minus 2z over 3. That would be the dot product of those two vectors. I should have written that first. Okay? So that is this part here, minus 2z over 3. Times dA, which we said was equal to 3 squared sine phi d theta. Okay, which is going to be equal to what? We're going to get minus 2, we're going to get minus, so 3 squared is 9, 9 divided by 3 is 3, 3 times negative 2, we're going to get negative 6 times z, and we're obviously using spherical coordinates here, so what is z? We look on our equation sheet, it tells us what the relationship between z and spherical coordinates. That is equal to a cos phi, where a is 3 in this case, so 3 cos phi, that's our z, sine squared of theta d theta. Oh my goodness, I made another, no, not squared. This isn't squared. It's this sine phi here. Sorry. Okay, do I have it straight now? Do you see any other mistakes? I think I'm good. Okay, so I replace z with its equivalent in spherical coordinates. So I get minus 18 cos phi sine phi d theta. What are the limits for phi and theta? 0 to pi by 2 for phi, because phi is the angle from the positive z-axis down, right? So obviously for half a sphere, if I integrate over that sphere, I'm going to go from here down to here, so 0 to pi by 2 for phi. Theta, I got to go all the way around, right, to get the whole half of the sphere, 0 to 2 pi. Okay, that's not a hard integral, right, because I can do a simple substitution, you know, make phi, because the derivative of sine is cos, so you can do that pretty simple. And that turns into a very easy integral, negative 18 pi. So I get the same thing. Okay, and we're done for today. So my plan on Wednesday is do a couple more examples of this. If you have any questions about other topics in the course, if you have any particular problems from quizzes, assignments, that you'd like me to go over in lecture on Wednesday, please send me an email, preferably by noon tomorrow, so I can get it all together. Okay, so if you've got anything you want me to cover on Wednesday, any examples, send me an email by noon tomorrow.